Hello, everyone, and today we'll talk about designing a query queue for ScyllaDB. My name is Avi. In the past, I've been working on Linux KVM as maintainer and primary author, the C framework, and today on ScyllaDB, a database which is based on the C framework. So usually when people present queues at such conferences, it's a single producer, single consumer queue or multi-producer, single consumer queue, which is hyper optimized for reducing the number of instructions and atomic operations and massive multiprocessing. And it has quite a lot of tricky code. And in fact, I've written a blog post on this very subject in the past, which I'm told is quite popular. And if my calculations are correct, it will now be posted in a comment on the side. But this is not about these kinds of queues. So while those usual single producer, single consumer queues use tiny amounts of memory, this queue manages megabytes per item queued. Those queues are typically very regular, using fixed size items, while this queue manages variable size items, can be from hundreds of bytes to many, many megabytes. Those queues, since they are hyper optimized for performance, they take just a few instructions per item, whereas this queue is really administering other operations. So it manages millions of instructions per item, at least potentially. Usually a single producer, single consumer queue is, its performance is measured in millions of operations per second, whereas this queue is not as performant. It only manages about 10,000 of operations per second per vCPU. And while usually those queues talk about CPU, this queue is concerned about CPU and I/O. So superficially, they're similar, but they're actually very different. So to frame the presentation, I'll explain a little about ScyllaDB. I'm guessing most of you are already familiar, but it is a horizontally and vertically scalable database. And horizontally means that if you run out of space or run out of compute power, you add more nodes. And vertically means that it will scale when you have larger and larger nodes. And in today's hardware environment, where you have hundreds of vCPUs on a node, it's important to be able to make good use of them. It's using the thread-per core C framework, which is the key to its vertical scalability. And it's, in terms of API, it's compatible with Cassandra and with DynamoDB. So let's talk about the ScyllaDB read path. Again, this is an overview. So ScyllaDB has a symmetric architecture where all of the nodes have the same roles. There's no metadata node or data node. So all of the nodes are symmetrical. And each node has two roles. One is as a coordinator, where it coordinates queries, and a replica manages the actual data. So a request would arrive at the coordinator from the client, so typically, say, a select query. It would then get replicated to two replicas in order to find the data and heal any discrepancies. And then the responses are sent back and merged and sent to the client. In this talk, we'll focus on what happens in the replica, and we can practically ignore everything else. So what happens at the replica? First, the response size can be very variable. You might be selecting a row that has a few dozens of bytes, so say a key value schema, or you might read 100 rows that are some number of kilobytes or thousands of rows that are smaller. And we try to target a page size of 1 megabyte in order to avoid expensive requests or complex requests. And it might even return 0 rows. And this can happen if the query result is empty or if we're processing a long list of tombstones. So all results are possible. The amount of effort that's involved in a query is also very variable. So it could be as simple as looking up in a cache, finding the row and returning it, or we might need to merge the data from multiple data sources. We can buffer some data that's on its way to disk in a mem table, and we will also read data from disk and files called SS tables. And these reads involve index lookups first. So we have a combination of parallel lookup within multiple SS tables, and within them sequential I/O for reading the index and reading the actual data. The timeout can be variable. So a user might ask for an important query to be completed quickly, and it will lose interest in it within, say, 100 milliseconds. So it might request a timeout of 100 milliseconds. But other queries, it might be happy to let a longer timeout in order to have higher chances of the query being successful. Some queries are more important to the end user, and some queries are less important, and we will also have to take that into account. And the queries are not continuous. So if you're doing, say, a select star from table, and you're reading the entire table, we're not going to read the entire table into memory and return it. We're going to divide it into pages and return each page in a single query. So we will need to consider that as well. So the first question is, why queue at all? We can start, and indeed we did start, without any queue. As soon as the request arrives at the RPC endpoint, we just let it proceed, and all of the requests run in parallel. One advantage is that you don't lose any time sitting in a queue and waiting for something to happen. So potentially you can utilize all of the resources. But very quickly after we tried that, we found the problems. And if the workload is simple, if you're hitting cache a lot, and if you're reading 100-byte rows, then everything is fine. But if you're reading multi-megabyte pages and you're hitting multiple files on disk, then each such query can consume a large amount of memory, and eventually you can run out. And the other problem is that the queries are competing with each other. So if you have, let's say, every query would take 100 milliseconds on its own, and if those queries are time sharing or sharing the disk performance with each other, and you have 5 of them, then they will all take 500 milliseconds. So where one would have completed in 100 milliseconds, now we have to wait half a second. And if the timeout is set below that, it means that all of the queries will time out instead of some of them actually succeeding and some timing out. And when we do time them out, we throw away all of the partial work that we've been doing. So not only did we time out, we also wasted resources not accomplishing anything. So we set out to fix it. The simplest possible solution is to just have a limit of one query executing at most, and all of them in the queue. So this will not run out of memory, because a single query, at least usually, will not consume all of the memory in the machine. The latency for that particular query will be low, because it's not competing against anything. And if any query that is waiting reaches its timeout before starting execution, we can just yank it out of the queue without any cost. So without spending resources, we can fail it quickly. But this doesn't work because the disk is going to get underutilized. So the disk can sustain a lot of parallel I/O and needs this parallel I/O in order to give you good performance. And this won't happen with a single query. And while the query is waiting for I/O, the CPU is going unutilized. So you don't want the disk and the CPU to be unused. You want them to work for you. And we knew this, so we didn't even try it. We started with something a little bit more complicated. So what we did was start with a semaphore instead of a simple queue. And the semaphore allows 100 queries to execute in parallel. On the diagram, I have 2, and the rest wait. So this gives the ability to saturate the CPU and saturate the disk. So we don't have the problem that our resources are idle, but it mitigated the main problem, but it didn't solve it completely. So again, if you have 100 queries and each use 10 megabytes, that's a gigabyte of memory. And again, 100 queries can easily compete with each other and not allow any of them to finish because they're all fighting for the CPU. So we wanted to fix the out-of-memory problem. So what we did was add memory accounting. And here, every time we allocate memory for the query, we track it. And every time we deallocate it, we also account for it. So at any point in time, we know for a particular query how much memory it is using. And the semaphore now, instead of just counting the number of executing queries, it only allows queries to run if there is enough memory available at the time the query started. And yes, it can happen that the memory can grow later, but it's usually not a problem. So typically a few queries will start, consume some memory. It will go over a little bit, but not. It's usually not a problem. Let's take a slight detour and go to the topic where we talked about paging queries. So long-running queries are paged at the coordinator level, and instead of returning millions of rows, we cut the query into 1 megabyte pages, which could be some thousands of rows. And each time we return a page and ask the client to continue later. The problem with that is that if we don't do anything, we will have to look up the index and reconstruct the query state. And all of the read aheads and prefetches that we did are basically lost. So what we did here is cache partial queries. We have an ID that is assigned by the coordinator, and it's also sent to the client so that we know how to keep track of it. We don't need to store the state anywhere. And when a query comes, when the next page is requested, we can look up in a query cache the query from the previous page and just complete from the point where we left off. So this saves the index lookup, and the disk buffer, the disk I/O for the data is also saved. It wastes some memory because we need to store those buffers in the cache, but this cache can be evicted when we run out of memory, and it's also evicted when some time passes. So I think it uses about 2% of the node memory. Previously I talked about how usually running a little bit over the memory threshold isn't too bad, but usually isn't good enough, and it is possible to run out of memory even with those memory limits. So we added an out of memory killer. It's similar to the one that you have in Linux. When some process goes wild and allocates too much memory, then the Linux out of memory killer looks for the process with the highest memory usage and kills it in order to reclaim its memory, and hopefully the system is saved. So here we have something very similar, except it operates in two levels. In the first level, we just stop issuing new queries. This is what I described previously. Afterwards, if we reach a higher threshold of memory usage, we kill all of the running queries except one. So this is the sort of survival mode. One query at a time makes progress. It's going to be slow, but at least the system is not going to go down, and there will be some forward progress made. And if even that does not work, we just kill everything and protect the database from crashing. Maybe it's not very useful if it's not able to serve any query, but at least the administrator can log in and maybe fix something. It's not something that you would expect to see in production, but it's there to save the day if it happens. Let's take another detour and look at vCPUs versus disks. So vCPUs, a CPU only process one thing at a time. It's possible to make it process multiple things by time sharing, but it's not actually doing those things concurrently. And because of that, if you add more things to process in parallel, it's not going to make the throughput higher. It's going to make it actually lower because there is overhead in context switching. And the latency will increase. So if you're doing 10 things in parallel, the latency will increase by a factor of 10. And disks are different. Disks like having like to process things in parallel. And if you add concurrency to the disk, the latency will not increase by a lot, at least until it's saturated. And instead, the throughput will increase until it's saturated. Now, you may tell me that CPUs these days are more like this, and you would be correct, because now processors have a large number of vCPUs. So if you run things in parallel and distribute them on all the available vCPUs, you will get higher throughput. But from our perspective, we are a thread per core architecture, so a particular replica only runs on one vCPU, and we're multiplying all of the queries on that single vCPU. The other vCPUs on the node are serving different subsets of the data. So they have their own work to do and cannot help us. So keeping that in mind, we see that running things in parallel on the CPU is not helpful. We do want to add concurrency if we're waiting for disk, but if we are already CPU bound, then piling on more work will only make things slower. But we need to know whether we are in a situation where we're CPU bound or IO bound. So how do we do that? So we realize that the query is constructed in a sort of graph where we have a number of subtasks that are needed in order to accomplish the query. And we track each of the nodes in this graph. And for each node, we check if we are blocked on CPU or on disk, or if not. And if all of the nodes are blocked on disk, then we know that the CPU is going to be idle, and we admit one more query. And if not, if we do have nodes that are actively consuming CPU, there is no point in admitting more queries. They will just compete with each other. When you run this system with a cache-bound workload where everything is read from cache and you don't touch disk, it will serialize the queries. Only one will be processed at a time. And this improves efficiency. There is no context switching. The data cached is well utilized. And since the queries do not compete with each other, the early ones complete early and have less chance of timing out while executing. So remember, we want to time out queries while they're sitting in the queue and haven't consumed any resources yet. So what about I/O? I talked about how to schedule CPU. So for I/O, we delegate that to the C-star I/O scheduler. I had some previous talks about it in previous P99 CONF and in Scylla conferences. It's an interesting topic, but it's out of scope for this presentation. So in the beginning, I talked about how not all of the queries are equally important. And if we have a queue, then we could have a situation where an important query is stuck behind a less important query. And there are multiple solutions for that, but we chose to have multiple queues that compete with each other. So before, we invested a lot of effort in reducing competition between queries, but here we recognize that sometimes we do want queries to compete. Each such queue has its own memory reserve. It has its own CPU and I/O priority, which are managed by the C-star schedulers. And each of them operates in the way that I described previously. So they're not really aware of each other. And this allows wildly different workloads to run in parallel without disturbing each other. Or rather, we want an online transaction processing workload to disturb an analytical workload without being disturbed in turn by the analytical workload. So some gotchas. Not everything worked as planned. In fact, nothing worked as planned. Everything that I've described was the result of problems we saw in the field and had to come up with fixes. So sometimes we have a situation where a sequence of queries can consume a very different amount of CPUs, even though from the point of view of the user, they are similar. So they would all be in the same queue, but sometimes a particular query would, when it starts executing, it would just dominate the CPU and not let anything else in. And if those queries are rare enough, then it is helpful to let them compete, because then the queries that don't take us much time can just sneak in while they compete and complete ahead of the long-running query. So the solution to that was just to chicken out and introduce an override that allows us to increase the CPU concurrency back. And it's rare. It's rare that we have to use it, but of course, when it does happen. It's for an important customer. We should have thought of it earlier, but of course, we only discovered it in the field. So to conclude, database queries are complicated. This has been a multi-year effort, not all at the same, not continuous, but it has taken us a long time to get it right. While it is intended for a high performance system, it's more focused on administrative tasks like accounting for memory and accounting for CPU, and not actually moving the data around. And we will probably continue working on it in the future as well, as we continue to refine the solution. So that's it from me. Thanks everyone for listening and watching.